Hey everyone, welcome back to Chem Story. Today we're jumping into a really important topic, nucleophiles and electrophiles. They're the key players in so many organic reactions, and once you understand how they work, you'll start to see reaction mechanisms a lot more clearly. But what exactly makes something a nucleophile? And what turns a molecule into an electrophile? Why do they behave the way they do? No worries, we're going to walk through all of it, step by step. And of course, I'll show you plenty of examples to make it all click. All right? Let's dive in. Alright, so first, what exactly is a nucleophile? A nucleophile is something that donates a pair of electrons to form a bond with an electron-deficient atom. But let's put it more simply, nucleophiles are electron-rich species, and they're naturally attracted to positive charges. First up, let's look at oxygen-containing nucleophiles. Water is a mild nucleophile. It's not super reactive, but it can still participate in reactions under the right conditions. Alcohols are a bit more nucleophilic than water. Now, if you take away a proton from them, things get more interesting. You end up with hydroxide ions and alkoxide ions, and these are much stronger nucleophiles because they carry a full negative charge. Another good example is the carboxylate ion. It's resonance stabilized, which means its negative charge is spread out over multiple atoms. Even so, it can still act as a nucleophile in the right kind of reactions. Now let's switch gears and talk about sulfur-containing nucleophiles. Sulfur is in the same group as oxygen, but it's less electronegative. That means it holds onto electrons more loosely, and that actually makes sulfur-based nucleophiles even stronger. For example, hydrogen sulfide and thiols behave a lot like water and alcohols, but they're more nucleophilic. And just like with oxygen, if you remove a proton, you get the conjugate bases HS- and RS-, which are the sulfur versions of hydroxide and alkoxide. These thiolate ions are super reactive because of their full negative charge. Next, let's take a look at nitrogen-containing nucleophiles. Nitrogen has a lone pair of electrons, so naturally it can act as a strong nucleophile in many reactions. Amines are especially common. You'll see them all over substitution and addition reactions. Other good examples include hydrazine and hydroxylamine. Both are pretty reactive. Now, if you go one step further and take away a proton, you get amide anions, R2N-, and these are even stronger nucleophiles because they carry a full negative charge. One more worth mentioning is the azide ion N3-. It's small, linear, and surprisingly reactive, and it plays a major role in click chemistry and other important organic reactions. Alright, now don't forget about halogen-containing nucleophiles. We usually think of halogens as electrophiles, but that's not always the case. Some halide ions, especially the larger ones, act as excellent nucleophiles. Take bromide and iodide, for example. Because they're bigger and more polarizable, they're more willing to donate their electrons, making them great nucleophiles in the right context. Alright, now let's talk about carbon-based nucleophiles. These are super important in organic chemistry because they're the ones that help form carbon-carbon bonds. First up, we have carbanions, carbon atoms that carry a negative charge. They're highly reactive and play a central role in many carbon-carbon bond-forming reactions. A great example of carbanions in action is organolithium reagents and Grignard reagents. In both cases, the carbon bonded to the metal behaves like a carbanion. It's electron-rich and ready to attack electrophiles. Another great example is the acetylide ion. It comes from alkynes, and it's a powerful tool for building new carbon-carbon bonds. And don't forget about enolates. They're formed from carbonyl compounds, and they show up in all kinds of important organic reactions. So why are organolithium and Grignard reagents such strong nucleophiles? It all comes down to electronegativity. Carbon is way more electronegative than lithium or magnesium, so in a carbon-lithium or carbon-magnesium bond, the electron density actually gets pulled toward the carbon, not away from it. And that makes the carbon highly nucleophilic, ready to attack electrophiles in a heartbeat. Next up, let's talk about hydride nucleophiles. These play a big role in reduction reactions because they deliver a hydride ion directly to an electrophile. And most of the time, that electrophile is a carbonyl compound. Two of the most common hydride donors are sodium borohydride and lithium aluminum hydride. Sodium borohydride is milder. It's usually used to reduce aldehydes and ketones. Lithium aluminum hydride, on the other hand, is much stronger, and it can even reduce esters and carboxylic acids. Alright, moving on to phosphorus-containing nucleophiles. The classic example here is phosphines. They've got a lone pair on phosphorus, which makes them really useful in organic synthesis. One of the most important reactions related to phosphines is the Wittig reaction, a powerful method for forming carbon-carbon double bonds. In this reaction, a phosphine reacts to form a phosphorus alide, and it's that alide that acts as the key nucleophile, attacking carbonyl compounds to build new CC double bonds. And finally, we've got pi-electron nucleophiles. So far, we've talked about lone pairs and negative charges, but don't forget, pi electrons in alkenes and aromatic rings can also act as nucleophiles. This becomes especially important in electrophilic aromatic substitution, or EAS. In that kind of reaction, an electron-rich aromatic ring reacts with an electrophile. And this concept is key to building lots of important aromatic compounds in organic chemistry. Alright, now that we've covered nucleophiles, let's switch gears and talk about electrophiles. If nucleophiles donate electron pairs, electrophiles do the exact opposite. They accept them. In other words, electrophiles are electron-poor species. They're on the lookout for extra electrons so they can form a stable bond. So, what kinds of molecules act as electrophiles? Let's walk through some common examples. Let's start with halogens. Even though we usually think of them as nucleophiles, they can actually act as electrophiles, especially when they carry a positive charge, or even just a partial positive charge. A great example is halonium ions, X+, where X is Cl, Br, or I. In certain reactions, halogens become electron deficient, and that makes them ready to accept electrons from nucleophiles. Now, what about oxygen? It's not always a nucleophile. In some cases, oxygen can act as an electrophile too, especially in peroxy acids like Ch.03. Peroxy acids are often used in epoxidation reactions, where an oxygen atom is transferred to an alkene, forming an epoxide. And sulfur? Same idea. In its protonated form, sulfur becomes electrophilic as well. A good example is protonated sulfur trioxide, SO3H+, which shows up in sulfonation reactions. Nitrogen-based electrophiles are also super common in organic chemistry. One of the most important is the nitronium ion NO2+. It plays a key role in nitration reactions, like the ones used to make nitro compounds. And finally, let's not forget the simplest electrophile of them all, the proton, H+. It's everywhere, from acid-base reactions to catalytic mechanisms. Since it has no electrons of its own, it's always ready to accept a lone pair from a nucleophile. Now, let's move on to carbon-based electrophiles. These are some of the most important ones in all of organic chemistry. First up, we've got carbocations. These are positively charged carbon species, and they're highly unstable and incredibly reactive. They show up in a wide variety of reactions, especially in substitution and elimination mechanisms. Then there's the acylium ion, RCO+. You'll often see this one in Friedel-Crafts acylation reactions. It's a key intermediate in many synthetic pathways. But here's the thing, not all carbon electrophiles carry a full positive charge. Some molecules don't carry a full positive charge, but they still act like electrophiles because of their structure. When a carbon atom is attached to a more electronegative element, like a halogen, oxygen, or nitrogen, it often ends up with a partial positive charge, and that makes it electrophilic. For example, in alkyl halides, CX bonds, the halogen pulls electron density away from the carbon, so that carbon becomes slightly positive and more reactive. You see the same effect in alcohols and carbonyl compounds. The oxygen withdraws electron density, making the carbon much more electrophilic. Even in nitriles, the carbon carries a partial positive charge because nitrogen is pulling electrons toward itself. Alright, so that's it for today's lesson. We covered the key ideas behind nucleophiles and electrophiles, looked at how they behave, and went through a bunch of useful examples. Understanding this will really help you predict how reactions happen and how molecules interact in organic chemistry. I hope this breakdown made sense. Thanks for watching, and I'll see you in the next one.